But now let's do something a bit more complicated. Let's do a triangle. And you're like, okay, triangle, I can solve for the forces on that pretty easy. But you're going to realize that the approach you take, right to left or left to right, is going to drastically simplify or complicate this process. So let's work through it. Alright, hopefully that's not too messy. Same setup. Over here we have x equals to L. We can quickly solve for our reaction force. I won't calculate moment because we're not going to use it here. But easily solve for a reaction. Ry is going to be equal to... Alright, now where were we? Ry is equal to, of course, W naught L over 2. Makes sense. It's half of what a rectangle would be for the same W naught. And of course W naught is just denoting the magnitude of that force as a function of x. You're going to see that, I think, as Newton over meter. Okay, so we have Ry. So now what we'll do is we'll draw the same diagram we drew last time. We'll draw that beam cut in half at any point and show what the loading criteria looks like. Should look something like that. But now there's a little trick here, because if I want to move if I want to move left to right, that's not a triangle anymore. That's a triangle on top of a rectangle. That's going to change the height of the triangle and the height of the rectangle as I move along the beam. It's a lot more complicated. But if I move right to left, I literally just have a triangle. So therefore, you're going to see in just a bit, it's a lot easier to work right to left in this case than it is to work left to right. So it does matter. Okay, same thing as before. We have x on the left and we have L minus x on the right. And intuitively that should make sense. Again, if our length is equal to L and we subtract x from it, that's going to be that distance, and the x we subtracted is that distance. Okay. Now, how do we characterize the force equilibrium here, left to right? So what we have to do is we have to identify what is this height of the triangle as we move in x. So what we'll do is we'll say, okay, we know it's going to be W naught. It has to be W naught when x is equal to L. Because as long as I have this full triangle, x equals to L, there is no little rectangle. So it has to be W naught at x equals to L. But when x is not equal to L, it's obviously not going to be that. It's going to be less. So what I'll say is if I take that W naught, I divide by L, and I multiply by x. At x is equal to L, I get W naught. When x is equal to 0, I get 0. Which makes sense because at 0, I'm basically at a very skinny, very tall rectangle. So that should make some sense. So what does this mean for the rectangle? Well, we know that the rectangle is going to be, the height's going to be 0 at x is equal to L. But when x is equal to 0, the height of the rectangle should be W naught. So what do we get? Okay. Then we should get something like this. W naught minus W naught x over L. When x is 0, we get W naught. When x is equal to L, we get 0. So these are the expressions for the distributed force. These are the expressions for the height of the distributed force. And now what we do is we do our force sum. So if we're moving left to right, sum of the force in the y equals to 0 equals Ry positive minus the triangle Now, remember, that was just for the height of the triangle. And if we're going to account for the base, remember triangle 1/2 base times height, we've got to also multiply by x over 2, right? Because that's the height, and that's base, and that's 1/2. So that's a triangle. Now we account for the rectangle, still acting downward, minus W naught minus W naught x over L multiplied by x minus v of x. It's quite long. There's a lot of stuff happening there. But have we accounted for everything? Here's the reaction force in the y, positive, minus the triangle. This is the sum of the force of the triangle, minus the sum of the force of the rectangle, minus v of x. So now we solve for v of x, we distribute our x over 2 in x terms, and let's see what we get. Okay, we end up with an expression that looks like this, and as you're going to see, these two x squared terms can cancel, so our final expression. Okay, now let's do our check. At x equals to 0, both of these terms drop out, and we get W naught L over 2, which is our y. That condition is satisfied. Now at x equals to L, this term here goes to W naught L over 2 minus W naught L plus W naught L over 2. So these two terms add to equal W naught L, then we subtract W naught L, we get 0. Now if you want to pencil that in, you can do the algebra on your own, but this here is satisfied at x equals to 0 and x equals to L with the boundary conditions that we have for the cantilever beam. Therefore, this is the correct expression. But you can see it was a lot more difficult to get to that expression than it will be when we do it from right to left here in just a bit. Because we had to derive what this height of the triangle was, what the height of the rectangle was as a function of x, as we move along the beam, because that changes. It was kind of a mess. But you can still get the correct answer, it's just a lot more work. So let's put this equation up over here. And let's go ahead and let's solve it from right to left. It'll be a lot easier. So the only thing we really need to figure out here is what exactly is this height of the triangle. Now we know that at x equals to 0, that height has to be W naught. And at x equals to L, that height has to be 0. So W naught divided by L times L minus x. This is the same thing we did before, but we're working in a different coordinate system. Now we have to use L minus x. That's going to be equal to the height of the triangle at any point x. How do you prove it? When x is 0, W naught L over L, L's cancel, we get W naught. X is 0, we get W naught. When x is equal to L, L minus L is 0, W naught over L times 0 is equal to 0. So there we go. This is the equation we're going to be using for the height of the triangle. Now all we do is our force balance, same as before. Remember, shear is positive here. It's going, or shear is in the positive y direction, that is. Okay, and remember, this is the height, this is the base, that is the 1/2. That's the equation for a triangle. So now all we have to do is solve this equation. Now that's a lot easier than solving it there. But does it still work? Let's check. When x is equal to 0, we get L squared here. W naught L squared over 2L, one of the L's cancels. W naught L over 2. W naught L over 2. That works. What about when x is equal to L? Well, when x is equal to L, L minus L is 0. 0 times W naught over 2L is 0. So it's satisfied. So this is another way to represent that shear force as a function of x. Simply solved it right to left. So hopefully that makes some sense. Now we're going to go ahead and we'll graph what this looks like. We'll graph what this looks like. Okay. Now it's quite simple. Again, we know we have to be at W naught L over 2 here. We know we have to be at 0 here. And the function itself is quadratic. So therefore, it's going to curve like that. It's not going to be linear, it's going to be quadratic. Now, if you really want to, I guess, prove this function, you can solve for one more point, typically at x over 2. So that's going to be L over 2. And we can plug that in anywhere here. Okay, W naught L over 8. So that's going to be about here. So my curve should be a little steeper. More like that. So you can solve for that third point if you want to, but typically, again, we're more concerned with what the max is, and we've just proven that the max, again, happens at the wall. Okay, now I know this was a bit of a longer video, but hopefully that makes some sense as to how we draw these shear diagrams. It's really not that bad. All you're doing is calculating what the sum of forces are at any point and solving for the internal force in the member. Remember, all you have to do is take your member and make an arbitrary cut at any location, expose the internal forces, equal and opposite on both sides, and you can solve it right to left or left to right, as long as you account for your boundary conditions. Now, they're going to give you problems, and you're going to see examples where, okay, now we have a beam, maybe that has a distributed force here. Maybe the Ry is already solved for. Then there's nothing. Then there's a point force at the tip. It doesn't matter. All you're going to do in your diagram is, again, in this section, you already know how to solve that. When there's nothing, it has to be equal to whatever it was at the end of here. We're not changing anything. And at the end there, you get a little bit extra. This is Ry. You go all the way till the end of that force, then you're held constant, and then you drop at the end because of P, where that height is equal to P. This triangle here is due to this, and this location here is, we'll call it region A. We'll call this region B. It's the same concept. You just decompose this and do force sums at the critical points. There's not much to it. So hopefully this explanation of making that cut in an arbitrary location on the beam, exposing the internal forces, hopefully that all makes some sense. You're going to see some different distributions, but the process is the same. If you have a distributed force, solve for the shear as a function of x. If you have a point force, then at that point you just get a little bit of an addition. It's just like the same as accounting for a reaction force. It's a constant, but it's only valid at that point, which is why you see those jumps in the graph. So hopefully this makes some sense. Please comment if you got any questions. Next week we're going to look at the moment diagram, which is a bit more complicated than the shear diagram. But if this makes sense, then we're going to get through moment as well. And that's going to be basically a key summary of what you learn in engineering statics. Now, again, remember why we care. Cantilever beams are typically how we will represent wing loading criteria. Now, the wing might not be loaded in a triangular shape. It might be loaded elliptical. It might be loaded parabolic. We don't know. rectangular, sometimes we take that approximation. But again, you'll know that from your fluids team. So as a structural team, as long as you know what your distribution looks like, as long as you know what the lifting force is on the wing, that's the distributed force, you can go ahead and calculate for how strong your material has to be at the support or at any point in the wing. What this does is it allows us to say, okay, if we have our diagram, let's jump back just a bit. I want to make one more point. Remember, basic curve. What this is saying is the internal shear experienced further out on the wing is much, much less than the shear experienced at the root. So therefore, we can save material weight, we can save material amount, all of that stuff, at the edge of the wing because that's not taking the load. That allows us to design for a wing where if I take a side profile, it might look like that, where it's thicker here at T1 than it is here at T2 because we don't need that added thickness at T2. We don't need that additional strength at T2 because that's not supporting as much of the load. So it allows you to make key observations like that, and that's how we decide. Again, let's say we taper a wing, right? Let's say from the top down the wing looks like this. That's fine given our loading criteria because we don't need this point to support as much, but this does. That's why it's thicker. That's why taper works. And you can make a lot of these assumptions, a lot of these analysis points by understanding how your internal forces are as a function of span length, or distance along the wing. And this is going to become even more crucial as we talk about moments. Because again, you're not just resisting a force, you're resisting a moment. But the moment diagram behaves roughly the same. And we'll talk about that next video. So again, sorry, this video was a bit longer than normal, but hopefully that clarifies a lot of the confusion about shear diagrams. So that's it for today, and I'll see you next video. Thanks for watching.